So far in the course, we've talked about distributions related to single random variables, whether they be discrete, like the binomial or the Poisson distribution, or they be continuous, like the exponential or the normal. But in order to make progress and understand the topic of statistics, we need to extend all of these concepts related to probability to more than one random variable. So now we need to extend the math to multiple random variables. And we'll denote these x1, x2, x3, etc., whether it's a finite list or an infinite list, whether the variables are discrete or continuous. So just for the purpose of clarity of illustration, I'm going to talk about multiple discrete random variables to begin with. And so the idea is that we are going to try and replicate as many of the definitions and concepts from single random variables as we can. So reuse the ideas of single random variables. So that means we are going to talk about things like probability mass functions, we are going to talk about expectation and variance. But in order to extend things, we will have to introduce a new idea. So to begin with, a mass function for, let's just talk about two random variables that are discrete. And here we'll illustrate it with just x and y. The mass function in this particular case is going to be a table. And the table here is going to have values of the probability. One entry could be listed one way. So for example, all the x values could be listed here, x1, x2, etc. And all the y values could be listed this way. So 1, 2, etc. And what ends up happening is we end up making a table. And within each entry, we will have a number that corresponds to the particular x value and the particular y value. So for example, we will be talking about what's seen on the PDF file attached to this video, the gas station example. And so here we're talking about self-serve versus full-serve islands and the number of hoses. So again, X will be the number of hoses in use on the self-serve, and Y will be the number of hoses in use on the full serve. So this mass function, as advertised, does end up being a table. And so the y values are going to be listed horizontally. There could either be 0, 1, or 2 hoses in use, and the x values are listed vertically. Same thing, 0, 1, 2. This table has 9 entries, and each value refers to a certain situation. And so just repeating what's listed on this form on the PDF file, we see that we make up several entries. Now, the point of the story, first property, is that if we were to sum up over all the I and j values, so pardon me, all the x's and y's, so if we say that the I index corresponds to x and the j index corresponds to the y's, if we were to sum up over all of them, we would in fact have to end up getting a 1. And this is a property of all mass functions that we want to persist even in the multivariable case here. So as I mentioned above, what we are trying to do is extend our ideas to this situation. So for example, if we are asked for something like the probability that x is 1 and y is 1, there's no work involved here. We just go to the table and look for the entry where x is 1 and y is 1. So it's pretty clear to see that this is just 0.2. We can get a little bit more involved with how the questions are asked. So for example, we could say, what's the probability that y is less than or equal to 1 as well as x? This needs to be translated into something that you can extract from the mass function. So this would consist of all entries where the x is less than 1 and the y is less than or equal to 1. So on this particular example, that corresponds to 4 entries. X is 0 and y is 0. X is 0 and y is 1. X is 1 and y is 0, as well as x is 1 and y is 1. So it's cumbersome to write, and we could end up using abbreviations. But in this particular situation, just to get the idea across, all we're going to do is list these values. So we'd end up getting 0.1 plus 0.04, 0.08 plus 0.2. So this would end up giving us 0.42. So none of that is horribly complicated. It's just getting comfortable with the notion of how a mass function works in the case of 2 variables. Now, we also want to talk about things like expected value and things like variance. But there are several issues that come up. We defined each of these things only for one random variable. So how are we supposed to deal with 2 random variables or more? And this is where a new concept gets introduced. And so what we have to do is talk about something called a marginal distribution. So a marginal distribution is in fact the tool that we're going to need to use to basically calculate these things. And in very simple language, this is what we're going to have to do is we're going to have to build a probability mass function for the x only and for the y only. Now, the reason this is called a marginal distribution is if you think of the previous example where we had x's and y's, and this is our mass function, the margin of a table is essentially just the end of one of the tables, whether it's vertical or horizontal. And so that name motivates what we are going to do to be able to calculate this. We are going to fix, for example, if we are going to be talking about the marginal distribution for x, we are going to fix each value of x and then sum over the y values. Now, in our example with the gas station, if we were to say something like this, the probability that x is 0, we are going to consider every case where x is 0 and then add up all of those situations for the different y values. And so in this case, we would get the following. We'd take the 3 entries where x is 0 and y varied, and we'd add them up. And so we would get 0.16 as the probability value for the one outcome where x is 0. Now, if I were to do the same thing for the outcome x is 1, I would take every outcome where x is 1 and then sum over the y's. So in this case, we are going to take the first entry to represent the x, the second entry to represent the y, and I'm being really lazy with the notation, but I think you can follow along. And we'll get 0.34. And finally, if we were to take that same gas station example and then sum over all the entries that have x is 2 and let the y values vary, we would get the following result. And so the marginal distribution for x is essentially the PMF for x only. That's what it is. And what I mean by that is we are going to build the usual old mass function that we've got. And so when x is 0, we calculated above that the probability was 0.16. We got 0.34 for when x is 1, and we got 0.5. And in this way, as always, these probabilities have to sum up to 1, which they do. And effectively what we're doing is incorporating all of the behavior of the y's into this so we can just see how the x's vary. And the reason we do that is because it now allows us to use our old definitions. So if we want to talk about the expectation, then we go ahead as we normally would. We would weight all of the outcomes by the probabilities, then add them up. And so in this case, we would get 1.34. So the expected value of the hoses in use in this particular case would be 1.34. And very similarly, if you're interested in the variance, it would be the expected value of x squared minus the expectation all squared. So in this case, it would be a summation of all the xi squareds times the probabilities. In this example, we would have 1.34 being squared. So just for clarity, this would be 0 squared times 0.16, 1 squared times 0.34, and 2 squared times 0.5. Subtract 1.34 squared. And if you're to go ahead and do this calculation, you'd get 0.594. So as far as obtaining values, it's relatively straightforward to do once you understand the notion of a marginal distribution. So again, the marginal distribution is the new idea for multivariable situations. Now, in the pre-lecture quiz, you're going to do the same for the y variable. You're going to build the marginal distribution. You're going to come up with the expectation for the y variable and the variance for the y variable. Now, the final topic that is of most interest to us is this notion of independence. Are our random variables independent? So for the discrete case, we are going to define independence to be the situation that if you were to take the full mass function, we call this the joint density. So if the joint density, if we have independent random variables, we would say that the situation is, well, when the random variable takes on these values, it should be equal to the product of the respective marginal values for those particular cases for all the outcomes. So this is another reason why the marginal distribution is important. In order to determine if these variables are independent, we are going to need to be able to take the individual outcomes and see if their product will hold. Now, for example, in our gas station, are x and y independent? It's going to turn out to be no. So part of this, again, you will need to do in your lecture video. But for example, when x is 0 from the marginal distribution, we will have 0.16. You will find that from the marginal distribution from y, the situation where y is 0 has a probability value of 0.24. The probability where x is 0 and y is 0 from the full mass function gets you 0.1, but this is not what you get when you multiply these two numbers above. And so in this sense, because I have found what's called a counter example, I have found one example where it does not hold. This implies that x and y are not independent. And the concept of independence is of paramount importance for us. And from this point, we need the marginal distribution. So in the next video, we'll talk about how to extend these things to continuous random